Okay, so so now I want to go on to another theorem. Okay, so this is one where we just have conditions on on individual jobs. Okay, so and so recall we've been using these row sets, these column sets CB as a candidate set or column set. So this is a set of people qualified for job B. That's the column set for B. And we discussed this before when we were kind of in our initial discussion of matching problems. Remember, RA is a set of jobs for which person A is qualified. So far we've only had conditions on on the column sets, but now we've got to have a theorem in which there's a condition on the row sets as well. Okay. So suppose you have a matching problem and an integer d bigger than 0. So firstly, we're going to assume that every candidate set has a size at least d. So for every job, there's at least d people who are qualified. And secondly, okay, so each person is qualified for at most d jobs. So the main claim is that every set's plausible, and therefore, by Hall's theorem, there exists a matching. Okay, so we're going to prove this to do a kind of proof by double counting. This is a fairly standard method of proof for a bunch of different things that we might consider. We're going to consider this set X. Okay, oh, what's actually that? Okay, so we want to prove, choose a subset of jobs. We need to prove that the number of candidates mod CU is at least as large as mod U. So now we're going to put X is the set of pairs A, B in A cross B, for which, let's say, so A is qualified for B and B is in U. So we're going to describe this set in a couple of different ways. Okay, so so we just one way to think about it, we sort of pick a job B that's in U and then pick a person that's qualified for it. So it's B's in U and A's in CB. And okay, another way we could describe it is as the set of pairs AB, where A is a person and B is a job that A is qualified for, and B is also in U. But let's just modify this slightly. Okay, so if B is in if we're in this kind of situation here, then there's A is qualified for B and B is in U, but that forces A to be in the set CU, right? If this kind of situation arises at all, then A has to be in the candidate set CU because A is qualified as B and then B is in U. Okay. So we're basically interested in these two descriptions here of the set. So using description 1, that tells us something about the size of X. Okay, so yeah, pick a point here, we pick our B, and then we choose our A and CB, so the size of it is a sum over all possibilities for B of the size of the set CB. But we know that the size of the set, yeah, we know that the set CB has size at least D. Okay, so that's at least, I can replace the CB by D, it's at least that, and that's D times the size of U. So that's one possible picture of the size of the set X. On the other hand, we can think about it this way. We pick a point A and then we pick a point B that's in RA intersect U. So it's equal to sum over A and A of the size of the set RA intersect U. And of course, this intersection is less than or equal to the size of RA. And we had our assumption, going back here, the assumption was that the size of RA is less than or equal to D. So the sum here is less than or equal to, so combining these, you've got D mod U less than or equal to the size of X less than or equal to D mod A, and D was strictly positive, so it's valid to divide by it. Oh, what did I say? Yeah, so I was supposed to be using relation 2 here. So A was actually in CU. Okay, so okay, so we divide by that to get okay, so we see from this that size of U is less than or equal to the size of CU, and that's our plausibility condition. And so Hall's theorem tells us that this problem has a solution. Okay, so now I'm going to do something rather similar, but just a tiny bit different. So again, we're going to suppose we've got a matching problem, the usual kind. Okay, so in this case, we're going to assume, so previously we were assuming that mod CB was greater than or equal to D, but so each job had at least D candidates. now in this theorem, we're going to assume that the size of CB is precisely equal to D. And then okay, so so then we're going to our second condition is going to be the same as in the theorem, that each person is qualified for at most D jobs. Okay, so let's consider people. Some people for which the size of RA is equal to D. Okay, so they've got so they have the maximum possible number of jobs that they can do. We'll call those people the talented people. So now our claim is okay. So firstly, I mean, these conditions already. I mean, by the previous theorem, I mean, we're saying CB is equal to D, but that actually implies that CB is greater than or equal to D. So so the previous theorem is applicable, and this means that there is at least one matching. But we want matching with an extra property. Yeah, so we claim that there exists a matching in which every talented person is employed. Okay. So, okay, well, let's assume the talented people are enthusiastic. And the untalented people are not. Okay, so that allows us to use the theorem about enthusiastic people. Okay, so we need to check the additional condition, the size of T intersect CU is at least as large as mod U plus mod T. So yeah, our theorem about enthusiast says that if we've got this additional condition here, then it's possible to do a matching in which every talented person is employed. Yeah. But if you go back to where we had the thing about had the theorem about enthusiasts, we stated this extra condition in a slightly different way. Yeah, so it was equivalent to this condition here, that the mod T less CU is less than or equal to mod B less U. In other words, this is the number of talented people who aren't qualified for any of the jobs we're currently considering, and this is the number of people. This is the number of jobs that we're not currently considering. Considering the jobs in U, B less U is the ones we're not currently considering, and these are the talented people who aren't qualified for any of the jobs in U. So we're going to prove this inequality by another kind of double counting argument, like the one that we did in the previous proof. So yeah, we're going to consider this set Y as a set of pairs A, B. So A is supposed to be a talented person, but actually A is supposed to be a talented person in T less CU in this set here that we're supposed to be trying to count. B is a job, and A is qualified for B. But yeah, so here, of course, so the main point to note here is that B has to be in B less U, right? Because A is qualified for B, and A is not qualified for anything in U, so B can't be in U. Oh, no, yeah. Okay. So let's think about the size of the size of Y. Okay. So it's the sum for over B. Okay, so we take the sum over all possible B's in B less U of the possible A's, the number of what are the possible A's. These are the people who are in T less CU and qualified for CB. Okay, but this is less than or equal to the sum over B and B less U, just of the size of CB. Okay, and remember the size of size of CB was equal to D for all B, so this is just D times the size of B less U. But looking at the other way around, so this condition here, A is in CB, is just the same as saying that B is in RA. Okay. So from this, we see that the size of Y is the sum over A and T less CU of the size of RA. Okay. But remember that A is talented here. So for the talented people, the size of RA is equal to D. So this is just D times the size of T less CU. Okay. So so we combine these two things, we get so D times the size of T less CU, that's the same as the size of Y, which is less than or equal to D times the size of B less U. Therefore, the size of T less CU is less than or equal to the size of B less U as required. Okay, so that's what we needed for the extra condition here. to be able to say that there's an allocation in which every talented person gets a job.